Welcome back. In our previous episodes, we delved into Retrieval Augmented Generation, or RAG, and Instruct GPT, two major innovations in language modeling. RAG really stood out for its ability to combine retrieval with generation, pulling in relevant data to improve factuality in real time. And then there was Instruct GPT, which brought a fresh approach to aligning model responses with human intent using reinforcement learning. Together, these episodes gave us a foundation in models that aim for higher accuracy and user alignment.
Right. And both those models gave us a look at specific improvements in the AI space, like making responses more factual with RAG or more user-focused with Instruct GPT. Now, we're diving into LLaMA, and it seems like there's a connection between these episodes.
Exactly. LLaMA builds on that foundation in a unique way. Instead of focusing on retrieval mechanisms or alignment tweaks alone, it tackles the broader issue of accessibility. LLaMA's creators aimed for an efficient, powerful model that could run on just one GPU, essentially making high-level language models more accessible for researchers everywhere. And what's cool is that it only uses publicly available data, which promotes transparency and reproducibility. A big step forward for the research community.
So, it's less about one specific improvement and more about a whole framework that's manageable and openly accessible, even to those without huge computational resources. That's a pretty big deal.
Absolutely it is. This episode is important because LLaMA doesn't just match up to models like GPT-3 in performance. Instead, it does so with far fewer parameters, which means it's computationally efficient and sustainable for wider use. It's not just an impressive model technically, it's a statement about what open and scalable AI could look like.
I like that. So, we'll get into things like how they made LLaMA efficient, the choice to use only public data, and how they managed to stay competitive with larger models. It's like they found a middle ground between power and accessibility.
That's a great way to put it. We'll explore the model's design choices, its impressive benchmark results, and even touch on its open-source license, which allows non-commercial research use. This way, LLaMA sets a new standard, not just for what these models can do, but for who can use and study them.
And I bet we'll talk about some of the challenges too, like how they handled bias and misinformation, since those are ongoing issues with large models.
Definitely, LLaMA isn't immune to these challenges, and we'll look at how it addresses them compared to previous models. Let's jump right in and start with the motivations and methods behind LLaMA. All right, let's dive into the abstract of this paper. It introduces LLaMA, which stands for Large Language Model Meta AI, a new collection of language models. These models range from 7 billion to 65 billion parameters, and they're trained on a huge amount of publicly available text data. The main idea here is that by using open data sources, LLaMA can match or even surpass other powerful models without needing proprietary datasets. So instead of relying on expensive or private datasets, LLaMA achieves high performance on available resources. That's quite the breakthrough for open access AI research.
Interesting. So, they're essentially making a powerful model that the research community can use without any data restrictions?
Exactly. And one standout example they mention is LLaMA-13B, a 13 billion parameter model that outperforms GPT-3, which has 175 billion parameters on most benchmarks. This means LLaMA-13B achieves comparable results with a model that's over 10 times larger. That efficiency is remarkable, especially since large models are usually costly to run.
Wait, how can a model with fewer parameters outperform a much larger one? Isn't more always better when it comes to AI models?
Good question. While it might seem that way, it actually depends on how well the model is trained and the quality of the data it's trained on. LLaMA's developers emphasize that training on a larger dataset of high-quality, publicly available tokens can lead to competitive performance, even with fewer parameters. In fact, smaller models trained well can be more efficient for tasks, especially when considering the computational cost of using them.
That makes sense. So, the key is the balance between model size and training data quality. And by using open data, they're also making the model easier for others to access and study.
Exactly right. And at the high end, their 65 billion parameter model performs similarly to the largest and most advanced language models out there, like Chinchilla and Paul-M. This model democratizes access to top-tier language modeling, aiming to make such capabilities accessible even on a single GPU. That's especially valuable for researchers and developers without access to huge computational resources.
Wow, I can see why this approach is important. It seems like LLaMA-S models could really lower the entry barrier for advanced AI research. Does the abstract mention anything about sharing these models with the public?
Yes, they explicitly state that all models in the LLaMA collection will be available to the research community. This open access approach not only encourages transparency, but also supports the development of fairer, more accessible AI. LLaMA is designed with the idea that anyone in the field can use it, study it, and contribute to its improvement, which is a big leap for AI development practices.
That's a refreshing shift from the usual closed-off nature of AI advancements. It sounds like LLaMA could have a huge impact on future language models.
Absolutely. The abstract highlights how LLaMA combines efficiency with accessibility, showing that with the right approach, we can achieve state-of-the-art performance without exclusive resources. This could pave the way for a more inclusive AI landscape. And that's the main takeaway from the abstract section. All right, now that we've covered the abstract, let's get into the introduction to understand the foundations and motivations behind LLaMA's development. So in the introduction, the paper starts by discussing the impact of large language models, or LLMs, on natural language processing tasks. These models have demonstrated an impressive ability to handle new tasks just from textual instructions or with a few examples. Can you think of why this would be a significant breakthrough in AI?
I guess it's because it means we don't need to train separate models for each new task. Like, the same model can adapt to different tasks without a lot of extra training.
Exactly. That's one of the key benefits. With the right scale, these models have achieved few-shot and zero-shot capabilities, meaning they can generalize across tasks without needing task-specific training. This property emerged when models reached a large enough size, which led researchers to prioritize scaling up these models as much as possible.
Right. I remember reading about models like GPT-3 and how they were trained with a huge number of parameters. But does this paper mention any drawbacks of making models bigger?
Yes, great point. While larger models can improve performance, the introduction notes that recent research, especially the work of Hoffman et al. In 2022, found that maximizing performance isn't only about increasing parameters. In fact, for a given compute budget, it can be more effective to focus on training smaller models with more data, rather than just adding parameters. This approach is called the scaling law, which guides how to optimize both model and dataset size within specific computational limits.
Oh, so the idea is to find a balance between model size and the amount of training data. That sounds like it would help make models more efficient, especially for researchers who don't have massive resources.
Absolutely, and this efficiency is crucial when we consider inference costs, how much it takes to run the model once it's trained. For instance, a smaller model trained on a larger dataset might take longer to train but ultimately cost less to use, which is a big advantage for widespread deployment.
I see. It's not just about how fast you can train the model, but also about how cost-effective it is to use in the long term.
Exactly, that's the point they emphasize. So the LLaMA project focuses on creating models that optimize for both training and inference efficiency by training on a vast amount of tokens, well over the usual datasets used for similar models. This way, LLaMA models perform well across a range of tasks while staying accessible for a broader research community.
That makes sense. So, does this mean they're using only open data for training LLaMA?
Yes, that's a unique aspect of LLaMA. Unlike many other large models that rely on proprietary data, LLaMA's training data is entirely from publicly available sources, which enhances transparency and aligns with open access goals. They mention that previous models like Chinchilla, Pal-M, and GPT-3 often include non-public data sources, which can limit reproducibility and open access.
It's interesting that they're focusing on open data. It feels like it could make a big difference in how the AI community engages with and builds on these models.
Exactly. By using public data, LLaMA provides a strong, open foundation for others to study and improve upon. The introduction ends by framing this model as a way to democratize access to advanced language modeling. Anyone with access to a single GPU, even if it's not particularly powerful, could experiment with LLaMA, especially the smaller models. This commitment to accessibility could lead to more innovation and fairer AI research practices. Now that we understand the motivations behind LLaMA, let's move into the approach they used to build this model. This section dives into how they trained the LLaMA models, and it's where a lot of technical choices and data strategies come into play. The training approach LLaMA uses is quite similar to some past language models, particularly those trained with large transformers, like GPT-3. They mention being inspired by the chinchilla scaling laws. These are essentially guidelines on the optimal size of models and datasets for maximizing performance within specific compute budgets. Why do you think they would need such a guideline here?
I suppose it would help them get the best performance for the resources they have. Instead of just making the model bigger, they can use these scaling laws to focus on how much data they need relative to model size.
That's right. And by following these guidelines, they can balance model size and data quantity to make sure they're not just throwing in more parameters without purpose. LLaMA is optimized for both training and inference efficiency, which makes it different from other models that might only focus on one of these aspects.
So, they're carefully planning for both training time and how easy it will be to use the model later. That would make it more accessible, wouldn't it?
Exactly. Their approach means that even the larger LLaMA models could be more accessible because they don't require extremely costly or prolonged training sessions. Another part of their approach is the choice of training data and sets. They opted for a combination of different public data sets, covering a wide range of domains. They've documented these sources and the proportions each contributes to the training data. Why do you think using a mix of diverse datasets could be important here?
Probably to ensure the model learns a broad understanding of language. By mixing different data types, the model could pick up on patterns from various contexts, which might make it more versatile.
Exactly. Diversity in data makes the model more robust and adaptable to a range of tasks. They use data from Common Crawl, C4, GitHub, and Wikipedia, to name a few, and each of these sources brings unique linguistic styles and topics. This mixture allows LLaMA to generalize better, especially on tasks it hasn't specifically trained on.
That makes sense. I'm curious about any specific techniques or optimizations they applied to speed up the training.
Good question. To speed up training, they made several adjustments, including using efficient implementations for multi-head attention and other optimizations that reduce memory usage and runtime. For instance, they implemented certain layers manually rather than relying on PyTorch's AutoGrad. This saved on computational resources, allowing them to use checkpoints more effectively by only recomputing necessary parts of the model.
Interesting. It sounds like they went deep into the code to make the process as streamlined as possible.
Exactly. They didn't just rely on default methods, but tailored the training setup to fit their needs. These kinds of improvements make a difference when training models at this scale. Spartans. This thorough approach helps them produce a highly efficient model, capable of competing with much larger, more resource-intensive models on various benchmarks. With that approach in mind, let's turn our attention to the main results they achieved with LLaMA and their instruction fine-tuning process. This part covers how well LLaMA performs across various tasks and how fine-tuning it on specific instructions improves its accuracy even further. The results start with a focus on LLaMA's performance on zero-shot and few-shot tasks, where the model attempts tasks with either no examples or a very small set of examples. The results here are pretty impressive. For example, LLaMA's S13B and 65B models match or outperform much larger models, like GPT-3 and Palm, on many benchmarks. Why do you think these tasks matter in evaluating a language model's capability?
I think these tasks are important because they show how flexible the model is. If it can perform well with little to no task-specific examples, it's likely better at generalizing across different tasks, which is useful for real-world applications where new prompts might come up all the time.
Exactly. Zero-shot and few-shot capabilities demonstrate the model's adaptability. And with LLaMA, they showed that the model could keep up with even the largest, most resource-intensive models. They also evaluated LLaMA on various benchmarks like common sense reasoning, reading comprehension, and mathematical reasoning. Across these, the 65B model consistently scored close to or even exceeded the state-of-the-art results, indicating it's highly versatile.
That's really impressive, especially considering LLaMA is trained on only open data. Did they mention anything specific about how the model's performance evolved over time?
Yes, they did track performance over the course of training. Generally, as the model trained on more data, its performance steadily improved on benchmarks like question answering and reasoning. This indicates the model's learning was consistent, which is a positive sign for robustness. They did notice, however, that on some datasets like social IQ-A, the results fluctuated, suggesting that specific benchmarks might be more challenging or less reliable as consistent performance indicators.
I see. So, overall, it's a solid performer, but some tasks may require further fine-tuning or specialized training.
That's exactly right. Speaking of fine-tuning, they conducted instruction fine-tuning as well. This involved training LLaMA to follow specific instructions, which led to rapid improvements, especially on the MMLU benchmark, a test for understanding in various domains like humanities, STEM, and social sciences. By fine-tuning with even a small set of instructional data, the model's ability to follow instructions improved significantly, making it more responsive to user prompts.
So, just by fine-tuning a bit on instruction following data, LLaMA could understand and respond to a wider variety of tasks better? That sounds like it could make the model much more practical.
Yes, that's the benefit. Fine-tuning on instructions adds flexibility, helping the model understand and respond accurately to a range of requests. And interestingly, the LLaMA-I model, which is LLaMA after this instruction fine-tuning, performed better than many other instruction-tuned models in its size category on MMLU. This indicates that even a relatively straightforward fine-tuning approach can make the model more powerful and user-friendly. Now that we've looked at LLaMA's instruction fine-tuning, let's explore the critical area of bias, toxicity, and misinformation within the model. This section is key because it addresses the potential harm LLaMA could pose in real-world usage. The paper highlights that, like most large language models, LLaMA can amplify existing biases found in its training data, including issues like stereotypes and toxic content. They tested the model on various benchmarks to gauge the extent of these issues. Why do you think benchmarks are useful here?
I'd say benchmarks help provide a clear, standardized way to measure things like bias or toxicity. Otherwise, it might be hard to quantify how biased or harmful a model's responses could be.
Exactly. Benchmarks allow them to systematically measure the presence of biases and potentially harmful outputs. They use tests like real toxicity prompts, which exposes the model to various prompts to evaluate its toxicity in generated responses. Interestingly, they noted that the larger the LLaMA model, the more likely it was to generate toxic responses. This aligns with other studies that suggest larger models can often amplify these risks.
That's concerning. So, does this mean larger models are always more likely to be problematic in terms of toxicity?
It's a trend that's been observed, yes, though it varies by model family and specific configurations. They also used another benchmark called Crow-S pairs, which examines social biases across different categories like gender, race, and religion. Here, LLaMA showed moderate levels of bias, particularly in areas like religion, where it had a higher bias score compared to some other models. The results suggest that while LLaMA performs well technically, it still carries notable biases.
It sounds like even with open data, bias remains a big challenge. Did they explore any other kinds of biases?
Good question. Yes, they also used Wino-gender, a test specifically designed to assess gender biases in CO reference resolution. For example, it looks at how accurately the model resolves pronouns in sentences involving gendered occupations. LLaMA's performance indicated some gender bias here too, particularly when the gender of the pronoun didn't match societal stereotypes related to certain professions. So, while LLaMA is more accessible and transparent in its data use, it's still impacted by underlying societal biases.
That makes sense. Bias seems really hard to avoid, especially if the data reflects real-world patterns that are biased to begin with.
Exactly. And beyond bias, they also assess the model's tendency to produce misinformation using the Truthful QA benchmark. This test focuses on factuality, checking how well the model can distinguish between true and false information across a range of topics. They found that although LLaMA performed better than some other models in this regard, it still showed a tendency to hallucinate or produce inaccurate information.
I see. So even with improvements, there's still a risk of generating misleading or incorrect information. It sounds like LLaMA has made strides, but there's definitely room for improvement in minimizing these issues.
That's right. They recognize that while LLaMA opens new doors with its accessible and efficient design, managing bias, toxicity, and misinformation remains essential. This area is challenging but crucial for ensuring the responsible use of AI models like LLaMA. All right, with a thorough understanding of LLaMA's approach and challenges in handling biases, toxicity, and misinformation, let's now look at the related work. This part provides context by discussing previous efforts and models that paved the way for innovations like LLaMA. The related work section kicks off by grounding language modeling as a fundamental problem in natural language processing, going all the way back to foundational concepts from the 1940s. Language models predict sequences of words or tokens, and they have evolved significantly over the years. Initially, statistical methods like n-gram models dominated. Do you know why these earlier statistical models would have been popular before the neural network era?
I think it's because they were simpler to implement and could handle basic probability distributions without requiring huge amounts of computational power. Neural networks hadn't become widely practical yet, right?
Exactly. Early language models relied on n-grams and simple probability techniques to estimate sequences of words. But as neural networks became feasible, more sophisticated models began to emerge, starting with feed-forward networks and eventually moving into more complex architectures like recurrent neural networks, RNNs, and LSTMs. Each of these innovations allowed models to handle longer text dependencies and gradually improved performance on language tasks.
So, it sounds like the models gradually developed from simple statistical methods to more complex neural network architectures as technology advanced.
Precisely. And then came the transformer models, which really marked a turning point. With the self-attention mechanism in transformers, models could capture much longer dependencies more efficiently than RNNs or LSTMs. This architecture, introduced by Vaswani et al. In 2017, laid the groundwork for today's large language models, including BERT, GPT, and now LLaMA. The self-attention mechanism was revolutionary because it enabled parallel processing of words in a sentence, which made training on large datasets far more practical.
That makes sense. I can see how transformers would allow for scaling up, especially with parallel processing. Did they mention other large models that inspired LLaMA?
Yes, they discuss several large-scale models that contributed to this field, such as GPT-2, BRT, and later GPT-3, which demonstrated the power of scaling in achieving few-shot learning capabilities. These models showed that simply increasing the model size and dataset could significantly improve performance. However, LLaMA's development was particularly influenced by Chinchilla and Palm. These models emphasized the importance of dataset size relative to model size, suggesting that large datasets can often yield better results than solely increasing parameters.
It sounds like LLaMA's approach was about balancing both the model and dataset size rather than just going for the largest possible model. Chinchilla and Palm seem to have helped refine this balance.
Exactly. LLaMA's design reflects those lessons by focusing on efficient scaling that maximizes performance within a specific compute budget, rather than just increasing parameters endlessly. This approach sets it apart from many earlier models that prioritized model size as the primary factor in achieving high performance. And with open access data, LLaMA also aims to push boundaries in transparency, which models like GPT-3 and PaLM, trained on non-public datasets, couldn't fully achieve.
So, LLaMA is both inspired by and a response to these earlier models, refining what's already been achieved, but with a focus on openness and efficiency.
Exactly right. This related work context highlights how LLaMA builds upon prior achievements in language modeling while addressing the need for accessible, efficient, and transparent AI research. It's this combination of influences and goals that make LLaMA unique among current language models. With the related work covered, let's wrap things up by discussing the conclusion. This section sums up the key achievements of LLaMA and outlines the broader implications for AI research. The paper concludes by highlighting that LLaMA offers a series of open, efficient language models that perform on par with some of the most advanced models out there. One big takeaway is that the LLaMA-13B model, which has just 13 billion parameters, can outperform GPT-3, which has 175 billion parameters on several benchmarks. What do you think is significant about this result?
It shows that we don't necessarily need a massive number of parameters to get good performance. LLaMA demonstrates that efficient training and dataset choices can achieve similar results with a much smaller model size.
Exactly. This efficiency also means that LLaMA models are more accessible for a wider research community, since they don't require as much computing power. Additionally, the LLaMA-65B model, the largest in the series, achieves performance that's competitive with models like Chinchilla and Palm, which are among the top-tier language models. By training only on publicly available data, LLaMA has shown it's possible to build state-of-the-art models without relying on proprietary datasets.
That's impressive. So, it could really encourage more researchers to develop advanced models without needing exclusive resources.
Exactly, that's the hope. The authors mentioned that releasing LLaMA to the research community could accelerate advancements in AI by allowing more people to explore large-scale language modeling. They also noted that instruction fine-tuning, as they tried with LLaMA, shows promising results, particularly for improving model accuracy on various tasks. They plan to continue exploring this fine-tuning approach in future work to further enhance the model's robustness.
So, they're aiming not only to build accessible models, but also to make them better at following instructions, which makes them more practical.
Exactly. Plus, they express interest in scaling even further by training on larger datasets to push performance boundaries. This ongoing development could lead to even more efficient models in the future. Altogether, LLaMA represents a major step toward making high-performance language models available and usable by the broader AI community. Well, that brings us to the end of our discussion on LLaMA. We covered some really fascinating points, from how LLaMA optimizes efficiency with fewer parameters to its use of open data, making advanced A/ETI more accessible than ever.
Yeah, it was great to see how LLaMA aligns with broader goals like transparency and accessibility while still performing impressively against models like GPT-3. It's definitely a model worth keeping an eye on as it evolves.
Absolutely. And I think the balance they struck between performance and accessibility is a trend we'll see more of, especially as the community pushes for open and responsible AI. Plus, their work on bias, toxicity, and misinformation provides a critical foundation for future improvements.
Definitely. Lots of food for thought here and exciting directions for anyone in the AI field.
Thanks for tuning in and exploring LLaMA with us today. We hope you enjoyed it and found it insightful. Until next time, keep learning and stay curious.